This example, we have y double prime minus x times y prime plus 2y equals 0. And we are going to find the power series solution about the ordinary point x equals 0. So the solution in the power series form will be in the form of the y equals summation cn x to the power n, and also from n from 0 to infinity. Also the y prime is in the form of the n times cn x to the power n minus 1, n from 1 to infinity. Y double prime summation n times n minus 1 times cn x to the n minus 2, n from 2 to infinity. We're going to substitute into the differential equation. The y double prime is the summation n minus 1 cn x to the n minus 2, n equals 2 to infinity, minus x summation of the n cn x to the n minus 1, n from 1 to infinity, plus 2 times the summation of the cn x to the n from 0 to infinity equals 0. Simplify the second term and the third term to be the summation n times n minus 1 cn x to the n minus 2, n from 2 to infinity, minus the summation n cn. Now the power of the x will become the power n as we multiply n to all terms, plus the summation 2 times cn x to the n from 0 to infinity for the last term. The last term, we replace n with the k, so no change. The middle term, same thing, change n into k. And the first term, change n minus 2 into the k. So let k be n minus 2, or k plus 2 equals n. We do this because we are going to rewrite all the power as x to the power k to all terms. The first summation now becomes the summation k starting from 0 to infinity. N is k plus 2. N minus 1 is k plus 1 times c subscript n now becomes c subscript k plus 2, x to the power k. Second term remain the same, just change from n to k. As well as the last term. From these three terms, the first summation starting at k equals 0, second one starting at k equals 1, and the last starting at k equals 0, we are going to find the common summation where k starting at 1. That means the first summation, we're going to take another term out as k equals 0 and write the rest as a summation for k starting from 1. So as k equals 0, the first summation will be 2 multiplied by 1, c2, x to the power 0, which is 1, plus the summation, now the index starting for k equals 1 to infinity, k plus 2 plus times k plus 1 times ck plus 2 times x to the power k, minus the summation k starting from 1 to infinity, k ck x to the power k, plus for the last term, we do the same way as what we did with the first summation to get the k equals 0 term out as 2 times c0 plus summation 2ck x to the power k equals 0, k equals 1 to infinity. Now, for the summation, we have all starting at the same k, which is k equals 1. That means 2 times C2 plus 2 times C0 as extra term plus the summation where k equals 1 to infinity and all have the same factor x to the power k. Coefficient of the first summation is k plus 2 times k plus 1 multiplied by ck plus 2. Coefficient of the second summation is k times ck, and the last coefficient is 2 times ck, with the common factor x to the power k equals 0. Next, we are going to equate the coefficient of the left and the right hand side. The right hand side is 0. That means the coefficient of each factor of each term gonna be 0. As we look at the left hand side term and the right hand side term, we can see that for k equals 0, 2c2 plus 2c0 equals 0, or we get c2 equals negative c0. We write the higher index in the term of the lower index. Next, for k greater than or equal to 1, we have the coefficient as k plus 2 times k plus 1 times ck plus 2 minus k ck plus 2ck equals 0. We're going to solve for ck plus 2, which is a higher index than ck. Or we say we rewrite ck plus 2 in terms of ck as k minus 2 multiplied by ck on the right hand side divided by the product of k plus 2 and k plus 1. And this is the recurrence relation for k greater than or equal to 1. For k equals 1, we obtain C3 as 1 minus 2 times C1 over 1 plus 2 times 1 plus 1, or negative C1 divided by 3 times 2, or negative C1 over 6. For k equals 2, and C4 as 2 minus 2 times C2 divided by 2 plus 2, 2 and 2 plus 1, or 0, which is nice. And next, for k equals 3, we obtain C5 as 3 minus 2 times C3 divided by 3 plus 2 times 3 plus 1, or C3 divided by 5 times 4. And C3 is negative C1 over 6, which is 3 times 2. Or we can see this as negative C1 divided by 5 times 4 times 3 times 2, or 5 factorial, where we can see the 6 as 3 factorial. And we see the pattern of the factorial coming out from each ck using the recurrence relation. Next, for k equals 4, we obtain C6 or from 4 minus 2 times C4 divided by 4 plus 2 times 4 plus 1. Since C4 is 0, C6 will be 0 as well. For k equals 5, we have C7 as 5 minus 2 times C5 divided by 5 plus 2 times 5 plus 1, as we have 3 times C5 divided by 7 times 6. C5 is negative C1 over 5 factorial, or we can see this as negative 3 times C1 over 7 factorial. As you predict for the k equals 6, we gonna get C8 equals 0 because we use the C6 as part of the formula. For k equals 7, C9 is 7 minus 2, which is 5. C7 divided by 7 plus 2, which is 9, times 7 plus 1, which is 8. And again, the C7 that we obtained from the earlier part is negative 3 over 7 factorial times C1. And we see the pattern as negative 5 times 3 times C1 over 9 factorial. The new number from the letter k is in the odd terms, so we can predict that for the k as an odd number, we have the numerator as a product of the odd term or the odd factors, and the sign alternate back and forth. No, sorry, the sign is not alternate, so the sign is going to be negative. Next, we're going to put them all together as a power series solution. As y x is c0 plus c1 x plus c2 x squared plus c3 x to the third and so forth. So yx equals, assume c0 is not 0. Otherwise, we're going to get the trivial solution. Assume c0 not 0. So then we can obtain the c2 as a non-zero term. So 0, c0 plus c1 times x, and the c2 as negative c0 times x squared plus the c3, which is negative c1 over 3 factorial times x to the third plus c4. C4 is 0, that means 0 multiplied by x to the fourth, and the c5 is negative 3 c1 over 7 factorial x to the fifth plus 0 times x to the sixth, and for the seventh term gonna be plus negative 5 times 3 times c1 over 9 factorial times x to the 7 and so forth. As we group them together as a common C0 and common C1 as a factor, for the C0, we have C0 times 1 minus x squared, and the rest of the terms will be 0 for the even power, plus C1, common factor of the quantity x minus 1 over 3 factorial x to the third minus 3 over 7 factorial x to the fifth minus 5 times 3 over 9 factorial times x to the 7. If you predict the next term, that would be negative 7 times 5 times 3 over 11 factorial times x to the 9 and so forth, as the power series solution form of this differential equation. So we can treat the first one as the first solution y1, and the next expansion, the series expansion here, as the second solution y2.